video we're going to go over how to do material balance with reactant systems. So we're going to use the extent of reaction and conversion. So the extent of reaction is how far a reaction has progressed. It's denoted by this symbol. The conversion is also a measure of how far a reaction has progressed, and you can calculate it through this. So if we do an example, so a mixture containing 40% of ethylene in terms of moles, and 48% oxygen, 12% inerts. Inerts are things that don't react, and they're fed into a reactor where the ethylene oxide is produced by the reaction. So we're given it. An undesired side reaction, complete combustion of ethylene, also occurs in the reactor. The conversion is 75%, and the yield is 55%. Determine the composition of the product. So this is the product. So I've drawn a schematic diagram of what's happened. So this is the reactor, you could say. So we have input of 40%, like we were given in the question, 48 and 12, which I've written here. I've chosen a basis of 100 moles because you need to choose a basis when you're dealing with material balance problems, given that these are compositions. So we're allowed to choose a suitable basis. We've got the two reactions, the main reaction and the side reaction, and we've wrote down all of our products. So because a big indication that we have all these products is that the conversion is not 100%, that means all of the reactants aren't converted into the products. That means you're still going to have reactants like oxygen and ethylene in the product. So that's how we know we have so many. So what I'm going to start by is I'm going to be writing down all of the moles of the products and working out the extent of reactions using the initial moles. So we have N1, N2, N3, N4, N5, and N6. So N1 is ethylene. Now at the beginning we had 100 times 0.4 because ethylene was 40% of the 100. So 40% of 100 is 40. So that's what we had at the beginning. And then ethylene reacted in this reaction. So we're going to call it the extent of reaction 1. And you multiply the extent of reaction by the stoichiometric coefficient because it goes through that reaction. So this is the extent of reaction 1, because we don't know if that reaction completed. So we don't know if all of the ethylene reacted, which is why we denote it by the extent of reaction 1. Now, ethylene also reacts in the side reaction. Even though it's undesired, it still reacts. So the coefficient of ethylene here is still 1. So minus extent of reaction 2. Now we do the same for all of these species. So oxygen, we're given 100 moles and 48% of it is oxygen. So we have 48 moles of oxygen at the beginning. Oxygen reacts in the first reaction, so we have a half minus a half, extent of reaction 1. And oxygen also reacts in the second reaction, and the stoichiometric coefficient is 3. So minus 3, extent of reaction 2. And we continue for ethylene oxide. So we're not given ethylene oxide in the beginning, which means it's generated, which it is in the first reaction. So because it's only generated and the stoichiometric coefficient is 1, that means the number of moles that come out, that is ethylene oxide, is just the extent of reaction 1, because how far the first reaction went is how much ethylene oxide could be produced, and because it's not used in the second reaction, then that's solely dependent on the first reaction. So for N4, carbon dioxide, we're not given any carbon dioxide, and we produce some in the second reaction. So the moles of carbon dioxide produced in this reaction is 2 multiplied by the extent of reaction in the second reaction, because it's not in the first, so it's only dependent on the second, and the stoichiometric coefficient is 2. If we do the same for N5, so water, we're not given any water here, and we produce some in the second reaction. So because it's combustion, it would actually be vapour, but it would still be H2O. And we see the stoichiometric coefficient is 2, so again this is 2 multiplied by the second extent of reaction, because we're going to call this the second reaction and this is the first reaction, right? And that corresponds to the extent of reactions. For N6, N6 is inert, so as we mentioned before, inerts don't react, so we still have 100 multiplied by 0.12. So we still have 12 moles of inert, which is fine. So now, what we're going to do is we need to find the extent of reaction 1 and the extent of reaction 2. So we're going to use the conversions that were given in the yield to work out the extent of reaction 1 and 2. So if we look at the conversion is 75%. Now what this means is 75% of the ethylene that was introduced reacted, 75% of the ethylene converted. So if we draw what it is, so 40, which is what we were given in the beginning, 100 multiplied by 0.4, 40 multiplied by 0.75, because 0.75 reacted, which is the conversion, that gives us 30, right? 75% of 40 is 30. So that means 30 moles of ethylene reacted. This means, by simple maths, 40 minus 30 equals 10. That means 10 moles did not react. And we have moles of ethylene outside coming out. And the moles that come out are the moles that didn't react. So that means N1 equals 10. We know that because we use the conversion to calculate the amount of moles that did not react, which allows us to form an equation here. So we still can't work out extent of reaction 1 or 2 because we have too many unknowns and we only have one equation. So now we can use the yield, which was given here. So the maximum moles of ethylene oxide that could be produced were 40, right? Because we were given 40 moles of ethylene at the beginning, and yield is a measure of what was actually produced over the theoretical amount that could have been produced. So because the stoichiometric coefficients are the same for this first reaction, had it been a theoretical reaction, so the reaction was done to completion with no side reactions, then if we had 40 moles of ethylene and we have 1 on both of them, that means we could have made 40 moles of ethylene oxide theoretically. So we can use that because we know the yield to find out the moles that reacted. So we have 40 multiplied by 0.55, 55% yield gives us 22 moles that reacted. So 22 moles of the 40 that were given in this equation reacted. And another way to express the moles reacted in an equation is by the extent of reaction, which we're already familiar with. So now we've worked out the extent of reaction for the first equation, we can use that to find the extent of reaction for the second one. So using the moles for ethylene, for example, we have 40 minus 22, which we've just calculated, minus the extent of reaction for the second reaction equals 10. we rearrange to find the extent of reaction for the second reaction. 40 minus 22 minus 10 gives us 8. So now we have the extent of reaction for the first reaction and the extent of reaction for the second reaction. So now we just substitute all of them into this and we have our composition of our products. So if we do that, we have N1, which is the moles of ethylene. We have 40, oh actually we've calculated it to be 10 already, 10 moles. So N2 we have N3 all the way to N6, which we know is 12 moles because it's inert. So N2 is 48 minus a half extent of reaction 1, which is 22, minus 3 multiplied by the extent of reaction 2, which is 8. So the moles of oxygen are 13. We do the same for the rest of the products. So N3 is just the extent of reaction for reaction 1, which is 22. N4 is 2 times the extent of reaction 2, which is 16. And same goes for N5, which is carbon dioxide and the water vapour. And that's how you do that's how you do material balance with reactant systems. That's it.